Concentration of X, Y and X2Y are 4, 2 and 2 moles respectively. The value of Kc for the equilibrium 2x plus y giving me X2Y is A, B, C or D. How do you work this? All this while we are discussing about what is the equilibrium constant, what are the factors that govern the equilibrium constant. Let us work this numerical. You are aware to calculate equilibrium constant, we take it up like this. I write Kc, that is equilibrium constant, is it is the product of the molar concentration of the products to the product of the molar concentration of the reactants, meaning it is the ratio of the product of the molar concentration of the products. I have concentration of X2Y by it is the product of the molar concentration of the reactant, that is concentration of X and concentration of Y. I have it raised to the power 2 times, that is X is raised to the power 2. Now, as a substitute, let us solve this. You are aware equilibrium constant formula. Now, on substituting the given data, I have concentration of X2Y, which happens to be 2 divided by concentration of X happens to be 4, therefore I write 4 square into concentration of Y happens to be 2, therefore 2 and 2 get cancelled. I have 1 by 16, 1 by 16 is equal to 0.0625. Therefore, the correct answer is option B, 0.0625. Our next question, to which of the following Ostwald's dilution law is applicable? Let us understand what is Ostwald's dilution law. Ostwald's dilution law is applicable only for weak electrolytes. Ostwald's dilution law gives the relation between degree of dissociation and dissociation constant of a weak acid or a weak base. Keeping these 2 points in mind, let us try attempting this. To which of the following is Ostwald's dilution law applicable? Option A, acetic acid, it is a carboxylic acid. Option B, HCl. Option C, nitric acid. Option D, sulfuric acid. So, here in this HCl, nitric acid, sulfuric acid are strong acids. Acetic acid is a weak acid. By default, all carboxylic acids are weak acid. Now, coming back to the question, to which of the following Ostwald's dilution law is applicable? Option A, acetic acid. Option B, HCl. Option B, nitric acid. Option D, sulfuric acid. Option A, acetic acid is the right answer. Option A is the right answer, and by default all carboxylic acids are weak acids. Our next question, the values of dissociation constant of acids at 25 degrees centigrade are given below. Identify the strongest acid in aqueous media. There is no working for this, a simple concept and a golden rule to remember. Larger the Ka value of the acid at a given temperature, stronger is the acid. Now, let us look in option A, B, C and D and find out which is having a larger Ka value. In the given option that we have, option A, B, C and D, option A is the larger value, therefore it is the strongest acid. Therefore, option A is the right answer. Our next question. The degree of ionization of a substance, option A, decreases with dilution, option B, increases with dilution, option C, may increase or decrease with dilution, option D, is not affected with dilution. You have to understand what is degree of ionization. Degree of ionization again refers to the fraction of the electrolyte that undergoes dissociation in aqueous media. The governing factor for the degree of ionization is, another factor is dilution. With increase in dilution, degree of dissociation or degree of ionization increases. This is one of the governing factor for degree of ionization. Another factor, increase in temperature increases the degree of ionization. One more factor, the presence of another electrolyte or a strong electrolyte having a common ion decreases the degree of ionization. I mentioned three governing factor. Dilution, with increase in dilution, degree of ionization increases. Increase in temperature, degree of ionization increases. Presence of a strong electrolyte having a common ion decreases the degree of ionization. Now my option here are relevant only with reference to dilution. Therefore, as I read the option, degree of ionization of a substance decreases with dilution, increases with dilution, may increase or decrease with dilution. Option D is not affected with dilution. The correct answer is option B, increases with dilution. Our next question. The equilibrium which remains unaffected by pressure change is. Before I tell what is the right answer, let us analyze what is the concept behind this. For all the equilibrium steps that you have in option A, B, C and then D, one governing factor which decides whether pressure has a role to play or not is to calculate the number of moles of the gaseous products and the reactants. The rule is like this. If the number of moles of the gaseous reactants is equal to that of the gaseous products, then pressure has no effect on the equilibrium. If the number of moles of the gaseous reactants is more than that of the products, high pressure would favor the equilibrium process, or high pressure would favor the forward reaction. If the number of moles of the gaseous reactants is less than that of the gaseous products, then low pressure would favor the forward reaction. Now keeping this in mind, let's try to analyze. In option A, number of moles of the gaseous reactants that I have, 1 and 1 happens to be 2. Number of moles of the gaseous products that I have happens to be 2, 2 and 2. The number of moles of the gaseous product is equal to the number of moles of the gaseous reactants. Therefore, option A is the right answer. I am repeating. The number of moles of the gaseous reactants is equal to the number of moles of the gaseous products. Therefore, option A happens to be the right answer. Let's also look into the other options that we have. In option B, again, analyzing in option B, the total number of gaseous reactants that I have is 2 plus 1, 3, whereas that of the number of moles of the gaseous products happens to be 2. The number of moles of the gaseous reactants is greater than that of the product. Therefore, high pressure would favor the forward reaction. Then what about option C? The number of moles of the gaseous reactants happens to be 2. Number of moles of the gaseous products happens to be 3. Low pressure would favor the forward reaction. Therefore, once again, a quick recap. If the number of moles of the gaseous reactants is equal to the number of moles of the gaseous products, pressure will have no impact at all. If the number of moles of the gaseous reactants is less than the number of moles of the gaseous product, low pressure would favor the forward reaction. And finally, if the number of moles of the gaseous reactants is greater than the number of moles of the gaseous product, then high pressure would favor the forward reaction. Our next question, pH value of decinormal solution of NaOH solution is? Very interesting question. They ask you to calculate the pH, but they have given decinormal NaOH solution. For a NaOH solution, you can calculate pOH. First calculate what is the pOH of NaOH solution. After that, using the relation pH plus pOH is equal to 14, we can arrive at the answer. Let us solve this. I am aware I am being given decinormal NaOH solution. Therefore, I know that pOH is equal to negative logarithm of hydroxyl ion concentration, which is equal to negative logarithm of, because it is decinormal NaOH, understood that it is 0.1. 0.1 happens to be 10 power minus 1. Therefore, I get pOH is equal to plus 1 minus of log of 10 power minus 1. I am aware of the concept. Log of a power m is m log a. Therefore, I get pOH is equal to plus 1. Now, using the relation pH plus pOH is equal to 14, I get it like this. Therefore, my pH will be equal to 14 minus 1. Therefore, pH is equal to 13. Hope you have understood. Therefore, pH of decinormal NaOH solution happens to be 13. In the option that we have, option A 10, option B 11, option C 12, option D 13, option D 13 is the right answer. Our next question, a solution of acetic acid in water contains. We are aware acetic acid is a weak acid. It undergoes partial ionization in water. When acetic acid is dropped in water, acetic acid undergoes dissociation to form acetate ions. In aqueous media, there is acetate ions, H plus ions that are being formed due to the dissociation will also combine with H2O that is already present in aqueous media. H plus ion that is produced due to dissociation combines with the water molecules to form H3O plus, that is hydronium ion, and also there is OH minus ion present in the solution. Therefore, the right contents of the solution of that which contains acetic acid in aqueous media is acetic acid, which is undissociated, acetate ions which have been produced in water, H plus ions which have been produced because of the dissociation combining with the water molecules to form hydronium ion H3O plus, and also there is a presence of OH minus ion. Therefore, the right answer is option C, CH3COOH, CH3COO minus, H3O plus and OH minus. The right answer is option C. Our next question. if ionic product of water is 10 to the power of minus 14 mole per liter the whole square, what is the hydrogen ion concentration of 0.1 molar in NaOH solution? What is ionic product of water? Ionic product of water is the product of the molar concentration of H plus ion, OH minus ion in aqueous media at 298 Kelvin. The value of ionic product of water as given here 10 to the power of minus 14 mole per liter whole square is given you the data for OH minus ion concentration which is 0.1. What is the H plus ion concentration is asking you. So, if you could decipher what is ionic product of water, I write it as H plus ion concentration, OH minus ion concentration is equal to 10 power minus 14 mole per liter the whole square. Now, is given the data for OH minus ion concentration is asking you to calculate what is the H plus ion concentration which is 10 power minus 14 divided by OH minus ion concentration which is 10 power minus 1. I get the answer as 10 to the power of minus 13 molar. I repeat, I get it as 10 to the power of minus 13 molar. In the option A, B, C and D, option A 10 to the power of minus 13 molar is the right answer. Option A is the right answer. Our next question. The solubility of A2B3 is S mole per liter. Its solubility product is relation between solubility product and the solubility is given by the simple logic expression that I happen to teach you now. Aware of this. You have an expression AXBY whose solubility is, I will say, S mole per liter. Its KSP expression would be, write it like this, KSP expression would be, it is x to the power of x, y to the power of y, s to the power of x plus y. Remember this simple concept. Now let's try for various options and come back to my question. I have it as AB2. Therefore, my KSP in this regard would be s to the power of x, it is 1 to the power of 1, that is nothing but 1, I don't need to write, I will just mention it here. Y to the power of y, it is 2, 2 to the power of 2 which happens to be 4, 1 into 4. I have s to the power of x plus y, 1 plus 2 happens to be 3 which is nothing but 4s cube. Hope you have understood. Now let's go back to our question. It is A2B3. Concept is very simple. My KSP in this regard would be x to the power of x, 2 to the power of 2 which is nothing but 4 into y to the power of y, that is 3 to the power of 3, 3 to the power of 3, 3 into 3 which happens to be 27 into s to the power of x plus y, that is 2 plus 3 which happens to be 5. So 27 into 4 happens to be 108. My right answer is 108 s to the power of 5. In the given options that I have, option A, B, C and D, option D 108 s to the power of 5 is the correct answer. Our next question. The least stable hydride of group 15 is, you are aware of elements of group 15, nitrogen, phosphorus, arsenic, antimony and bismuth. all these elements of group 15 undergo reaction with hydrogen to form hydrides. These hydrides are of the type EH3. E happens to be the element here. Now if I happen to write the hydrides of group 15, I write it like this: nitrogen, the first element of group 15, hydride of nitrogen, ammonia, ammonia, phosphine, PH3, nitrogen, phosphorus, arsenic, that is hydride of arsenic, ASH3, nitrogen, phosphorus, arsenic, antimony, hydride of antimony is SbH3, stibine, and finally I have BiH3, which is bismuthin. Hydrides of elements of group 15, nitrogen, phosphorus, arsenic, antimony, bismuthin, these are ammonia, phosphine, arsine, stibine and bismuthin. In this, the rule is like this: as I move down the group, the stability of hydrides decreases. That means the most stable hydride of group 15 happens to be ammonia, while the least stable hydride of group 15 happens to be bismuthin. So you got the answer now. Most stable due to the presence of hydrogen bonding is ammonia because of its nearness to the nucleus. As I move down the group, I am moving away from the nucleus, distance increases, stability decreases. Therefore, least stable hydride of elements of group 15 happens to be BiH3, which is bismuthin. Option D, BiH3 is the right answer. Our next question: the ratio of electron, proton and neutron in tritium is, tritium or tritium, however you read it as. There are three radioactive isotopes of hydrogen which you should be aware. One is 1H1, this is protium, 1H2 deuterium and 1H3 tritium or tritium. In this, you are aware the number of protons in all of this happens to be one and the same, it is 1. When the number of protons you are aware, the number of electrons will also be one and the same. The number of neutrons is arrived at, it is the difference between the mass number and the atomic number. Therefore, here if I happen to write for protium, the ratio of electron is to proton is to neutron, it is 1:1:2. The number of neutron is 1 minus 1, which is 0. Come back to the next one, deuterium. It is 1:1:2. 2 minus 1 is 1. Come back again for tritium, 1H3. It is 1:1:2. 3 minus 1 is 2. Now my question: the ratio of electron, proton and neutron in tritium is 1:1:2, that is option B is the right answer. And one more important point about this tritium 1H3, it gives away beta rays. Our next question: H2O and H2O2 resemble in which of the following options? Let's try to understand this concept. H2O and H2O2. In both of them, the elements are hydrogen and oxygen. You are aware, water is a bent molecule, while hydrogen peroxide has got an open book structure. Therefore, they differ in their structure. So option C is ruled out. Come back to bond angle. Water molecule is V-shaped bent molecule whose bond angle is 104.5 degrees, while hydrogen peroxide, in different phases it has got different bond angles. In a solid phase it's got a bond angle of 90.2, whereas in gaseous phase it has got a bond angle of 111.4 degrees. Therefore, it differs in its bond angle. What about the oxidation state of hydrogen? The oxidation state of hydrogen, the central atom in both this water and hydrogen peroxide happens to be, central atom is oxygen. The hybridization state will definitely be the same, but the oxidation state will vary. In water, oxidation state of oxygen happens to be -2, while in hydrogen peroxide, oxidation state of oxygen is -1. It differs even there. So, oxidation state of oxygen in all peroxides happens to be -1, while oxidation state of oxygen in water happens to be -2. Therefore, it differs in option B, it differs in option C, it differs in option D, and option A, hybridization of oxygen, both of them, central atom happens to be oxygen, hybridization state happens to be sp3. So, both of them have got sp3 hybridization, they resemble in hybridization state of oxygen. Option A, hybridization of oxygen, is the right answer. Our next question, electron precise hydride among the following is? To arrive at the answer, follow the following guidelines. Find the total number of valence electron. If you are able to link all the valence electron around the central atom with the surrounding atoms, it is electron exact. If there are lone pair of electrons, then it is electron excess hydride. By default, hydrides of group 13, that is boron hydride and aluminium hydride, are electron deficient hydrides. Now we will look into the option. Option B, ammonia, has got one lone pair of electron. Therefore, it is electron rich or electron excess hydride. Come back to option C. It is a hydride of group 13. Hydrides of group 13, as I mentioned, boron hydride and aluminium hydride, are electron deficient hydride. Option D, water molecule, has two lone pair of electrons. Lone pair of electrons are those that are present but are not involved in the bonding. Even that happens to be electron rich hydride or electron excess hydride. Now let me confirm and then tell that methane, which is option A, is an electron precise hydride. How do I go about? Now, I am aware carbon, total number of valence electrons in this happens to be 4. I take hydrogen, 1 into 4 is 4. Total number of valence electron for methane molecule happens to be 8. Now, when I try to write the Lewis dot structure, I have carbon and then I have 4 hydrogen. I put it up accordingly. The rule says put a pair in between. Therefore, there are 8 valence electron. I am satisfying it. 1, 2, 3, 4, 5, 6, 7, 8. Total number of electrons available 8. Total number of electrons used up 8. Therefore, it exactly fixes according to the definition electron precise hydride. My correct answer is option A, methane is an example of electron precise hydride. Our next question. Decomposition of hydrogen peroxide is prevented by option A, KOH, option B, by the addition of MnO2, option C, the addition of acetanilide, option D, oxalic acid. Hydrogen peroxide is very much unstable. It undergoes decomposition. The decomposition can be retarded by the addition of underlining statement, textbook answer. The decomposition of hydrogen peroxide can be retarded, can be slowed down by the addition of acetanilide, which acts as a negative catalyst. Therefore, option C, acetanilide, slows down the decomposition of hydrogen peroxide. Option C is the right answer. Similarly, I have another option here, MnO2. MnO2 is an example of a positive catalyst. It influences the rate of decomposition of potassium chlorate. Potassium chlorate, KClO3, undergoes decomposition to form KCl and O2. By all means, the reaction is very slow. If I want to accelerate the decomposition, if I want to make the reaction go little further or little faster, I add MnO2. MnO2 acts as a positive catalyst, influences the decomposition of potassium chlorate, and here acetanilide acts as a negative catalyst, slows down the rate of decomposition of hydrogen peroxide.